Okay, let's jump right into this explainer. Today, we're demystifying the core philosophy and the actual mechanics behind designing modern, data-intensive systems. If you're building apps today, you know you're inevitably building distributed systems. It's just a fact of life now. So, understanding the absolute foundations of how to make them reliable, scalable, and maintainable, yeah, it's absolutely crucial. We're leaning heavily into the big ideas from Martin Klutman's incredible work here. So, let's get to it. Before we nerd out on architecture, I want to ground us with this thought from computing pioneer Alan Kay. He pointed out the awe-inspiring scale and reliability of the internet. It really is a marvel, right? I mean, we interact with these massive planetary-scale distributed networks every single day. And honestly, they're practically invisible to us. Well, until something breaks, of course. Our ultimate goal as engineers is to hit that exact same level of seamless reliability. We've got to treat scale not as this annoying hurdle, but as a foundational design parameter right from day one. To systematically break down these massive applications, here is our roadmap for today. We'll start with the data-intensive challenge, move into the 3 system pillars, look at the shift to distributed data, and then unpack the heavy hitters of scale, replication for redundancy and speed, and partitioning to divide the load. All right, Section 1, the data-intensive challenge. Let's start with the modern problem, the massive shift in what actually bottlenecks our applications today. So, here's the reality check. Raw CPU power, it's rarely the limiting factor anymore. We've mostly moved past compute-bound problems. Instead, we are constantly grappling with data-intensive applications. The real bottlenecks now are the staggering volume of data we have to store, the crazy complex relationships within that data, and the sheer velocity at which it changes. It's like trying to drink from a fire hose while simultaneously organizing a library. A single traditional database just isn't going to cut it for this stuff anymore. Which brings us to Section 2, the 3 system pillars. To actually tame this data-intensive reality, we have to rely on 3 foundational concepts to evaluate any system we design. Pillar number 1 is reliability. This is basically ensuring your architecture can survive the worst. And I mean a broad mandate here. We've got to account for hardware just suddenly dying, because it will, insidious software bugs, and, let's be honest, human error, which is probably the biggest wildcard. A truly reliable system builds in fault tolerance to essentially hide these inevitable failures from the end user. You want the app running perfectly, even if the servers in the back room are literally on fire. Next up, scalability. You know, you always hear people casually say, oh, that database doesn't scale. But scalability isn't just a binary yes or no thing. It means having a strategic, mathematically sound way to add capacity and deal with growth. It's about measuring your current load, whether that's a massive spike in reads or a flood of new data writes, and understanding exactly how your performance will degrade so you can provision resources long before things crash. The third, and honestly the most frequently ignored pillar, is maintainability. Look, you can build a highly scalable, rock-solid system, but if it takes a PhD to operate the thing, it's going to fail, period. As projects grow, they easily morph into this giant big ball of mud that just grinds engineering to a halt. Maintainability means designing clean abstractions, giving your ops team actual visibility into system health, and ensuring you can evolve the architecture later without having to rewrite the whole shebang. Moving on to Section 3, shift to distributed data. Let's look at how these pillars actually shape our physical architecture as we move away from massive, single mainframes to distributed, shared-nothing networks. The truth is, modern applications are essentially forced to become complex data systems themselves. You don't just have one master database anymore. You've got an in-memory cache for lightning-fast reads, maybe a full-text search index over here, and an asynchronous message queue over there. Your application code is sitting right in the middle, stitching all these distinct, purpose-built tools together and hiding that absolute chaos behind a nice, clean API. Once you start doing this, you're not just writing app code anymore. You are officially a data system designer. And since you are the designer now, you really need to internalize this. There is no magic scaling sauce. There is literally no one-size-fits-all generic architecture you can just copy-paste to get planetary scale. Sorry, it doesn't exist. Every single design choice you make is a trade-off that's hyper-specific to your app's unique bottlenecks. Are you read-heavy, write-heavy? Do you absolutely need strict consistency? Your answers to those questions dictate the entire architecture. That leads us to Section 4, replication for redundancy and speed. This is the first of our 2 twin engines of distributed scale. Welcome to Replication Island. This is a great way to visualize how we keep identical copies of data on multiple nodes. Why bother? Well, mainly to survive outages, so we don't lose data when a node inevitably bites the dust, and to serve way more users by spreading out the read queries. But looking at this map, you'll see we've got a few different territories: single leader, multi-leader, and leaderless. And yeah, each one comes with its own treacherous waters, like the pit of failover or the replication lag highway. A super common starting point is the single leader approach. Here, one primary node, the leader, handles all the write requests. It commits the data locally and then streams those updates out to its follower replicas. When a user wants to read something, they can just ask any of the followers, which takes a massive load off the leader. It's a very clean, organized way to do things. But, catch-22, if that leader crashes, the system has to scramble to promote a new one, and that operational hiccup can be pretty tricky to manage. And we see these trade-offs all across the landscape. While single-leader systems are great at carefully organizing the order of operations, leaderless systems, which, by the way, were heavily inspired by Amazon's Dynamo architecture, they totally ditch the concept of a leader. They let any node accept a write directly from a client. This is a real game-changer for availability, but it fundamentally shifts how we handle conflicts. It basically forces your application to figure out how to resolve conflicting data versions on the fly. All right, Section 5, partitioning to divide the load. If replication is all about duplicating data for safety and read speed, partitioning is about what happens when your data set just gets too astronomically huge to fit on one machine's hard drive. So now we navigate over to the partitioning atoll to explore sharding. This is where we intentionally break a massive database into smaller, totally independent subsets called partitions. Think of it like taking a giant, incredibly heavy phone book, ripping it into smaller chunks, and handing each chunk to a different server. By doing this, we distribute the storage burden, and we can spread the query processing load across tons of different processors all at the exact same time. But the million-dollar question is, how do you decide which piece of data goes to which server? Well, think of key-range partitioning like organizing a physical set of encyclopedias. It assigns a continuous span of data to a specific node, so Volume 1 holds A through B, Volume 2 holds C through D, and so on. It makes looking up related records insanely fast. However, if suddenly everybody on the internet starts searching for words starting with A, that first server gets completely hammered, creating what we call a dreaded load hotspot. Okay, let's put the whole picture together. As we split our data into partitions for sheer storage capacity, we simultaneously replicate those partitions across different nodes to guarantee high availability. It's super cool to see in action. Notice how Node 1 might act as the leader for Partition 1, but at the very same time, it's serving as a backup follower for Partition 2. It's this beautiful, intricate dance of distributed data, designed so that a single machine failure will never, ever take down your whole system. Ultimately, the real power of partitioning is that it lets us distribute both storage and compute. We can avoid those nasty load hotspots by tweaking our strategy, maybe using hash functions instead of alphabetical key ranges to perfectly randomize the data spread. And the truly elite systems, they dynamically rebalance. They just seamlessly shuffle partitions between nodes as you plug in more hardware, keeping everything running smoothly at a massive planetary scale. Because building these shared-nothing distributed architectures requires a constant, almost obsessive balancing of our three pillars: reliability, scale, and maintainability. There is no perfect silver bullet answer. Every choice you make to replicate data faster might cost you strict consistency. Every time you partition data for scale, you might make your complex queries that much harder to run. So as we wrap up this explainer, I'll leave you with this to think about. What trade-offs will you make in your next data system?